This is section 13.4, Methods of Expressing Solution Concentration. In this, we'll look at several different ways to express concentration of solutions, including mass percent, parts per million, parts per billion, mole fraction, symbolized with a big capital X, molarity, which we've already heard of, and molality, symbolized by a script letter M. So first, let's look at mass percent, parts per million, parts per billion. Mass percent is equal to mass of the part of the thing that we're interested in divided by the mass of the whole solution, usually measured in grams. Put both in the same set of units and then multiplied by 100%, part divided by whole. We often express the concentration of very dilute solutions in parts per million or parts per billion. These quantities are similar to mass percentage, mass of part divided by mass of whole, except we multiply by 1 million for parts per million or 1 billion for parts per billion. So parts per billion once again is the same as mass of the part that we're interested in divided by the mass of the whole thing times 1 billion. A solution whose concentration is 1 parts per million contains 1 gram of solute for every 1 million grams of solution, and 1 milligram of solute per kilogram of solution would be another way to say this. Because the density of water is 1 gram per milliliter, 1 kilogram of a dilute aqueous solution has the volume very close to 1 liter. Therefore, 1 part per million also corresponds to 1 milligram per liter of aqueous solution. So milligrams per liter many times is exactly the same as parts per million. Alright, let's take a look at sample exercise 13.3. I've got it over here on this side, and we'll work this sample exercise over here and talk through it for calculating mass percent and parts per million. So in part A, it says that a solution is made by dissolving 13.5 grams of glucose, which is C6H12O6, in 0.1 kilograms of water, H2O. What is the mass percent of this? Remember, mass percent is always equal to part divided by whole times 100%. And what we need to do is make sure that the part and the whole thing, these two added together, are in the same set of units, so the units cancel. So the top would be 13.5 grams, and the bottom would be kilograms, 1, 2, 3 for grams, 100 plus 13.5 grams, and then we'd multiply that by 100%. Running that through our calculator, we would end up with 11.9% for a mass percent for that 13.5 grams of glucose dissolved in 100 grams of water. Part B says a 2.5 gram sample of groundwater was found to contain 5.4 micrograms of zinc ion. What is the concentration of zinc in parts per million? Well, parts per million is the same as calculating mass percent of a solution, except for we don't multiply by 100, we multiply by 1,000,000. So we need to get both of these into the same units and then divide them. So parts per million would be equal to 2.5 grams. Whoops, 2.5 grams is our total. I'm sorry, I've got to put the part on the top. 5.4, and since this is micrograms, remember there are in 1 gram 10 to the 6th micrograms, because micro is 1 million times smaller than a gram. And so this would be 5.4 times 10 to the negative 6th grams. And then we would divide this by the whole thing, which would be 2.5 grams plus the 5.4 times 10 to the negative 6th grams. But this is assumed to be in this 2.5 grams because this was our sample of groundwater. And so this is already in the sample. So we don't need to add that in, and plus 10 to the negative 6th wouldn't add very much to 2.5. Then we need to multiply this by 1,000,000, so multiply this by 10 to the 6th, and 5.4 times 10 to the negative 6th divided by 2.5 times 10 to the 6th ends up being 2.2, and then we use ppm as the units for that, parts per million. Alright, the next type we're going to look at is something called mole fraction. And mole fraction is equal to the moles that are the part that we're interested in divided by the total moles in the solution. And we use a subscript right down here to indicate the thing that we want to know. Whatever part we're interested in, that's the mole fraction that we want to find. So for example, if a solution is 1 mole in HCl and 8 moles in H2O, calculate the mole fraction of HCl. Well, we take the mole part that we're interested in and put it on the top, 1 mole, and take the total moles and put it on the bottom. So that would be 1 plus 8 moles on the bottom. So 1 divided by 9 would end up being 0.111. And notice there's no units for this, and we'd say that this is our mole fraction of HCl. We use the little subscript HCl to indicate that's the substance that we're interested in the mole fraction of. Thirdly, we're going to look at finding molarity, which we've already done before. Molarity is equal to moles divided by liter, and molarity is equal to the moles of the part that we're interested in, the solute, divided by the liters of the total solution. And we've done that many times before. The last one we'll look at is molarity, and molarity is symbolized by a script letter M, a small letter m, and that's equals to the moles of solute divided by the kilograms of solvent. And so the difference between molarity and molality is similar enough that they can easily be confused. So molarity depends on the volume of the solution, liters right here, whereas molality depends on the mass of the solvent. When water is the solvent, the molarity and the molality of dilute solutions are numerically about the same because 1 kilogram of solvent is nearly the same as a kilogram of solution, and 1 kilogram of the solution has a volume of about 1 liter. The molality of a given solution does not vary with temperature because masses do not vary with temperature. The molarity of the solution does change with temperature, however, because the volume of the solution expands or contracts with temperature. Thus, molality is often used, and it's the unit of choice when the solution needs to be known over a range of temperatures. Let's look at sample exercise 13.4. Here's a solution that's made by dissolving 4.35 grams of glucose, C6H12O6, in 25 milliliters of H2O. Calculate the molality of the glucose solution, and it's telling us to assume that the density of the water at this temperature is equal to 1 gram per milliliter. So molality, once again, is moles of solute divided by kilograms of solvent. And so the first thing we need to do is take our grams of solute and convert it to moles. There are 180.2 grams in 1 mole of C6H12O6 when we add it up on the periodic table, and that equals 0.0241 moles of glucose. And then we'd have to make sure that this, our solvent, is converted to grams. And if density is equal to mass divided by volume, we can find the mass by taking our density, 1 gram per milliliter, times 25 milliliters, and we'd have 25 grams of solution. Notice it has to be in kilograms though, so when we find the molality now, we would do 0.0241 moles divided by the kilograms of the solvent, and grams to kilograms would be 1, 2, 3 to the left, or 0.025 kilograms. Dividing those two would give us a molality of 0.964, and then we use a script letter M to indicate molality. Alright, the last one we're going to do is a sample exercise 13.5, where we have to calculate and change between some types of concentration measurements. So it says in sample exercise 13.5, an aqueous solution of hydrochloric acid contains 36% HCl by mass. 36% HCl by mass. Calculate the mole fraction of HCl. So it wants to know the mole fraction of HCl. It wants to know the molality of the HCl. And a third one, calculate the molarity of this solution. So by knowing the percent, how can we find all three of these other methods or other ways of expressing concentration? So first plan, when you're given the percentage by mass of something, know that that's part divided by whole. And you can always take this number and write it over as a percent or as a decimal, and it's always easy to make an assumption of a 100-gram sample of the solution. If you make an assumption of a 100-gram sample of a solution, now we have 36 grams of the thing that is the percent, the part, and it would be 100 minus 36 of that part that would be the solvent, or the other item, in this case water. And so we'd have 36 grams of HCl and 64 grams of H2O. And now from here, to find the mole fraction, we would simply find the moles of these two and then divide them. So the moles of HCl, we'd take 36 grams, look up HCl on the periodic table, and take 36 divided by 36.5, and we'd end up with 0.99 moles of HCl. And then we'd have to find the moles of water, and adding up H2O on the periodic table, it adds up to 18.01 grams. So round it to 18, 64 divided by 18 is 3.6 moles of H2O. Now to find the mole fraction, we take part divided by the whole thing. And so the part would be 0.99 divided by the whole thing, which would be 0.99 plus 3.6, and then this would end up being 0.22 for our mole fraction. Remember, there's no units on mole fraction because the units here are mole and the units here are mole, and the moles would cancel with the moles. The second one is to find molality. Molality, remember, is equal to moles of solute divided by kilograms of solvent. And so we know the moles of solute right here is 0.99 HCl, and we know our solvent is 64 grams. And so to find this, we'd take 0.99 moles of HCl, and then we'd divide it by kilograms. And remember, this is 64 grams, so 3 to the left, 1, 2, 3 would be 0.064 kilograms of H2O, and this would turn out to be 15 molal. So now we found our mole fraction, we found our molality, and lastly, how do we find the molarity of the solution? Well, here's where the density of the solution becomes important, because to find the molarity, we have to take moles of solute, which would be this HCl, and divide it by liters. And you can find this by using the density triangle, because density is equal to mass divided by liters, which is a volume. And so if you want to find the liters right here, you can take and solve for V, and that's equal to the 100 grams of solution divided by the density, which we are told is 1.2 grams per milliliter, and we end up with 83.3 milliliters of solution. So now we have our moles, which is 0.99 from right here, and we have our milliliters, 3 to the left, 1, 2, 3 would be 0.083 liters. Divide those two, and we end up with about, to sig figs, 12 molar. And so you can see that molarity and molality are sometimes different, even though it's got the same stuff in it and they sound the same. That's an overview of several different ways to find concentration of solution.